Five, four, three, two, one.
Okay. Hello, willkommen, bienvenue, konnichiwa, jambo, ni hao, marhaba. Any more?
Bonjour.
Bonjour. It's time for the Armist Inquisition, yet again, episode 191 on Sunday, the 4th of July.
Yeah.
The day those filthy colonials threw off the yoke of the great British Empire.
Yeah.
And look what it got them.
I know, yeah, exactly.
Yeah, just world domination for, a couple of 100 years. Anyway, I'm Amish Phil.
I'm Amish Ben.
And I'm Amish Matt.
And we've got two guests for the price of one tonight. Mm-hmm. We've got Simon Shack and Patrik Holmqvist here to tell us about the Tychos model of the solar system. How are we doing, chaps?
Doing very well, thank you. Nice to be with you tonight.
Great to have you.
Mm. Yeah, doing just fine from Gothenburg, Sweden.
Oh, very good.
And from Rome, Italy, the eternal city.
Yeah, this is truly...
Actually in the countryside, outside Rome.
Cool. I would, I've never visited Rome, and I don't know why, because I'm just obsessed with the history and the Roman Empire and stuff. So
you should never meet your idols. Maybe that's it.
My idol, Augustus in the flesh. You're gonna have to take us on a tour, Simon, when I finally make it over there.
Oh, you have to come. I can host you all three of you. I have an old house, but it's pretty large. You can always find a bed.
You might regret saying that.
No, I'm used to that. I've been inviting scores of people over the years from all over the world.
Yeah.
Through my different research endeavors, I've invited people that really I wanted to meet. So you are invited.
Oh,
thank you.
Excellent.
Yeah, you guys are invited.
We're ready to have our paradigm shattered because,
Yes.
We like new ideas, alternative explanations for the phenomena we find around us. And this is why, this Tychos model that primarily you've developed, Simon, but Patrik has been helping you with the software and the program, which we'll see a little later on.
Yes, exactly. I'll just tell you shortly the story. I mean, I was finishing my manuscript of the book, and by chance, I would right at the time I was actually looking here in Italy for someone who could help me make some kind of simulator, in a digital interactive planetarium. But then I was right in those days. As I finished my manuscript, I was invited to Sweden to present another research of mine, which we won't go into here. But when I got there, I was hosted by Patrik in his house. He was the guy who had an available guest room, basically, and I started talking with him about my ongoing astronomy research. And initially, Patrik, I think you remember you were a bit skeptical.
Yeah, this is why is he talking about this? No.
Yeah, I mean, I could fully appreciate that, because I had just been sitting here like crazy for a few years, like already, well, at that time maybe 3 or 4 years. Working on my model, and Patrik was the first guy I really showed the manuscript to, and he said, okay, but maybe I could help you. Later on, he mailed me and said,
I honestly brushed it off at the time, but I got your manuscript, and I I told myself, I thought this can't be it. I mean, I know your other research is correct, but this was just too much. But then I went on vacation, and I had your manuscript in my tablet, so I started reading it, and I understood that even though I didn't, think it was correct, I understand that I can't refute this, I can't falsify this. So it may, but and how can I do this? Or I can help you out because I wanted to find myself. I can help you out with the computer modeling. And so if I do that, I will help you, and I would find out for myself if it if it works. And now a couple of years later, I'm very convinced. Yes.
Yeah, well, it was absolutely amazing to me. Maybe one of the highest, highlights of all this research was when Patrik sent me his first installment, his first version of this simulator, the Tychosium, which is actually a planetarium, which shows how the whole system works. Because I'd only been imagining it, in my mind and writing stuff about it and calculating. But I was, of course, eager to, but very nervous to try it out, to make it work actually. How would you say? I mean, physically, because it's even if it's a digital planetarium, it's a physical thing, and you have things moving around, and they have to move as I was predicting. And the first version was really immediately. It looked like it was working. I mean, the main thing was the movements of Mars, because Mars. Let's start with. Let me now just do a very short historical little overview of who Tycho Brahe was. Tycho Brahe. I've been basing my model on Tycho Brahe's model, which was a very, very important model in the 16th century. It was actually for 100 years accepted as the best model over the Copernican. The Copernican wasn't immediately accepted. Very few people know that, but for 100 years, Tycho Brahe's model was the accepted one in Europe. Because Tycho Brahe was a Danish nobleman, astronomer, who was a friend of the king, and the king gave him all the money he wished for. He built a castle with an incredible observatory, facilities. He made his own instruments, amazing armillaries to measure the distances between the planets in the sky, which is much more important than having just a telescope to point in one dot, right? He was looking at the big picture. So Tycho Brahe is universally recognized as the best observational astronomer of all times, still today. But Tycho Brahe, no one knows him. Almost no one has heard of him.
Have you heard of him?
Have you guys heard of him?
Not before seeing your emails in the Amish Inquisition Gmail account. No.
Yeah, everyone goes to Bruno, Galileo, Kepler, and Brahe's overlooked.
Exactly. And Kepler, you mentioned Kepler. You know who Kepler was? He was just a little mathematician who was invited by Brahe to his castle.
Yeah.
Or actually to Prague when he was kicked out of Denmark at one stage. He had to leave his castle, and he met Kepler in Prague because he became the royal astronomer in Prague. And this Kepler, who was a really, really weird guy, very, very strange guy. He was, half the years of Tycho. He was a kid. He was 25 and 26 or something when they met. And so Brahe just was. He was kind of impressed with his mathematical skills. So he said, I gave you I gave you my observations of Mars because they are the most problematic. And he said, oh, yes, sure. Kepler said, yeah, I'm going to solve this in 8 days. But it took him 5 years to finish his papers on Mars. He struggled with Mars the motions of Mars for 5 years. He was becoming mad. I mean, there is so much literature, and there are so many things you can read about. He wrote a lot to his fellow, researchers around the world to say how he was going crazy because Mars wouldn't fit into the model, into his idea. Now, please understand that Kepler was a Copernican. He believed in the Copernican idea that the Earth, is going around the sun, and he wanted to make that work. So he was like a traitor in Tycho Brahe's house.
Wow.
He was from the word go. But Brahe didn't really care about that. He said, "Yeah, Copernicus is a good guy, but my model is better." And what was Tycho Brahe's model about? Let's go straight to that thing.
Yep.
Tycho Brahe's model had the sun circling around Earth and Mars circling as well around Earth, but intersecting with the sun. So the orbits of the sun and Mars intersected. And all his peers at the time laughed at him because they were saying, well, if they intersect, they must be, sooner or later they will crash into each other.
Yeah.
Do you understand two intersecting orbits? I mean, you know that because you know the Taikos, but our listeners may be not understanding what I'm saying now.
Yeah.
But the orbits of Earth and the orbits of the Sun and Mars intersect.
I could do a screen share here
Yeah,
of the model,
let's see it.
so it's easier. The
Let's see it.
picture
Let's
says
start
more.
and
Yeah.
get an idea of what it looks like.
Let's see. Is it on screen? Guys?
It is, yeah.
So this is what Simon's talking about. You have here we have the sun, and we have the orbit of the sun and Mars intersecting across each other.
The sun is the yellow one and Mars is the red.
The furthest one out, the tiny one, yeah.
Yeah, and around the sun we have two objects, which are Mercury and Venus. Mercury and Venus are the moons of the sun. I call them, in my book, I just call them the moons of the sun because they are moons. Why are they moons? Because they are tidally locked. They show the same side. To anyone who stays on the sun, they will see the same side of Mercury and Venus all the time, just like we see the moon. So it's wrong to call them planets. We should call them moons. The moons of the sun are Venus and Mercury. And it makes absolute sense. And it actually explains one of the big mysteries that astronomers are still have still not solved. Why do Mercury and Venus not have any moons? All the other planets have moons, many moons. Jupiter has like 70 moons or 80, and Saturn has 90 moons, and all planets have moons, but Mercury and Venus. Well, my answer is they have no moons because they are moons. And no one has ever observed in our skies a moon that has a moon. Okay? No moons have moons of their own because they are already moons. So that explains one big thing straight away. But now let's look at where the Earth is placed. The Earth is placed in what could very well be the barycenter, even though Mars is much smaller than the Sun. But think about a very, very important thing. We don't know exactly how we know that the Sun is bigger than Mars in size, but the Sun we know, well, we think we know at least, that it's basically gases. It's made of hydrogen and helium, the two lightest gases we know of. The burning molecules of helium and hydrogen. So the Sun might be much lighter than we imagine, whereas Mars is made of rock and iron, right?
Yeah.
If we accept that these things are true, we might even say that even though they are very different in size, they might weigh the same amount of kilos or pounds, So just to get these things straight. But very quickly on this thought, I want to tell you immediately that what really started me on this research when I got away from, I was very timid in the beginning. I didn't know exactly should I go forward with this research. What can I add to this Tycho Brahe system and explain it? Well, I decided to look at the star Sirius. You know Sirius?
Yep.
It's the brightest star in our skies.
Yep.
And you know that in very late, not very long ago, they found that Sirius had a companion.
Sirius B, yeah.
Sirius B. But no one knew that, and Tycho Brahe didn't know that either in the 16th century. He had no idea that binary stars existed. And the binary star is it just means that a star has a companion, like a husband and wife. And the smaller one can be very, very much smaller than a big one.
Right, so Sirius B is a lot smaller than Sirius A, is it?
A lot smaller. They call it the the puppy, they call it, astronomers, because it's that small. And that was a big problem when they found Sirius B for Newton's theory, because he, if that little thing was circling and intersecting orbits with its main star, it should have been sucked up immediately, in Newton's theory. So what did they come up with? Well, they said, Sirius B there must be some, it must be 400,000 times more. There must be 400,000 times more gravity on Sirius B than on Earth. It must be really heavy. The atoms must be so packed together that everything on Sirius B weighs 400,000 times more than on Earth. Right. That's how they got out of the quandary, of the problem. They had a big problem with Sirius B. So they did establish that Sirius B, they came up with an ad hoc explanation that Sirius B must be extremely dense and packed with, and that's why it is so heavy that it can go around this huge Sirius A, okay? So I just went to Wikipedia at the time to see what is the diameter that they reckon Sirius B is and what is the diameter of Sirius A. And do you know what I found?
Go on.
The proportion between Sirius B and Sirius A is practically identical to Mars and the Sun.
Right.
Mars is 0.48% the size of the Sun, and Sirius B is 0.48 the size of Sirius A. 0.5, if you like, to make it simpler. Both are 0.5% of their big mother, okay?
That's quite a coincidence.
That's quite a coincidence. I mean, and Sirius is, it's not the closest star; it's the fifth closest, but it's the biggest we have, and it's a very important star. And then, please understand now that in the latest 20 years, they have found that almost all the stars have a companion. Almost all this. I'm sure that 100% are binary, but they are saying officially already that 90% are binary.
Wow.
And they're saying that some others we haven't, but the others they just haven't found. Probably because they haven't found a small companion because they are too small sometimes.
Right. And the relationship between the small star and the big star makes it, if that ratio is even greater, it makes it harder to detect, I guess, because.
Yes, and get this. Our closest star, Proxima Centauri, they discovered in 2016 that it had a companion. Right. Yesterday they discovered that. And our next closest star, or second or third closest, the Barnard star. Barnard star is a very fast-moving star. They discovered in 2018 that it had a companion. So you can imagine that. That's why they're saying only 90% are, because many others haven't been detected with the best telescopes we have. So I'm saying very, very confidently that all stars are binary, which makes it impossible. I mean, statistically, that our sun is the only bachelor in the whole universe. Okay? Yeah. It makes it statistically absurd, right?
Yeah. So I mean, just to frame it, Simon. I mean, the claim you make with your model is that Tycho Brahe in the 17th century was almost right with his model.
Yes.
And I mean that's what's and I think a very interesting and compelling thing with Tycho Brahe's model as opposed to the heliocentric model is also that it has what I would call physically plausible motion.
Mm-hmm.
This model only uses circular constant speed orbits. And the heliocentric model uses elliptical varying speed orbits.
Yes.
And I mean, if you do, I mean, you have a certain degree of freedom then. So I mean, the ellipses are squeezed and the speeds are adjusted. So it's observationally correct.
Exactly. And
Right.
for the former.
That was Kepler's fault.
Right. So you,
Well, please, just let me finish here. And the thing is that circular constant speed orbit, that's something that's experimentally reproducible. We can just have a magnet orbiting. You can reproduce this, but you can't really reproduce the kind of orbits that they claim occurs in the heliocentric model. Not in a lab experimentally, but I mean. And also, as you've been explaining here, I mean, as we observe and find out more things about our surroundings, a very common reasoning is as below, so above. We are seeing now that we have binary systems all around us.
Yep.
And a binary system, assuming we wouldn't be able to see the center object, would look just like a system. I mean, that is what Simon proposes, suggests that the solar system is a binary system just like any other system.
Yeah.
And this is how it would look. But I mean, and the key piece, I mean, the key piece you add to this as well, Simon, is your discovery and claim of the PVP orbit.
Yes.
That Earth is in the barycenter of the system, but Earth is also moving very, very slowly in an orbit.
Yes.
And what's so amazing with that is that when that is assumed, every observation we see around us, and particularly the precession, the stars slowly shift, very slowly. And this is explained by this simple second motion of Earth, because then we will only have two motions of Earth. We have an Earth that's circulating rotating every 24 hours, and it's moving slowly in its PVP orbit.
Clockwise.
Yeah, clockwise. And
so
this is still visible. I can show if
keep it
this
keep it this
is
way,
I mean, this is the year.
I wish to explain to the viewers.
Yeah, go ahead.
The basics now. Just keep it straight and don't make it elliptic. Make it flat. You know,
there we go.
Like this.
From above.
As you can see, all the orbits are perfectly circular, which was what for thousands of years all astronomers were trying to make come to a conclusion that because they naturally thought that those things going around us go in circles, but it didn't match with the better the observations got, they had problems with that. It didn't really match the observations. But here, this is the first, what you're looking at is the first ever planetarium that shows that it can be so, that all the planets have circular orbits and they go at the same speed. Now, I want to get back to my beloved Kepler, because he was such deceiver. He worked for 5 years in Tycho Brahe's house or castle, and he didn't he didn't. I mean, he called it his war on Mars. He got totally desperate because the more he calculated, the more he tried to make Tycho Brahe, his master's observations match with his maths, it didn't work. So what did he come up with eventually? He came up with two variables. Oh, Mars must be accelerating and decelerating along its orbit. Number two, the orbit must be elliptical, not circular. And so and then it matched with his master's observations, and he became world famous. Everyone knows Kepler. No one knows Tycho Brahe, but Tycho Brahe had made the correct observations. Okay, so he made that fit. And if you remember what you saw in school, they told you that the sun is in the middle and everyone is going around like a merry-go-round around the sun. It looks very nice, very elegant, if you will. It's a nice, it's a nice story. Yeah, sun in the middle and everyone going around like in a children's playground. Well, it's not it's not that simple. It's elegant, of course, but it is just a bit more complicated, but not so much. It's as you're looking now at the sun is going around the Earth, and Mars, its companion. The companion, which is circling around a circling object like the sun, will eventually do this kind of pattern. It will do a trochoid. The trochoid will make it at some stage as viewed from Earth. We will now see. Look at Mars now. Look at Mars, the red dot, reddish white. Now it will look from us, from Earth, to be stopping in its motion. It's now slowly stopping and then going backwards, and that's what we observe.
Retrograde.
Now it's a retrograde, and it lasts on average for 72 days. For 72 days, it will go backwards. It does that. It does that physically.
Yeah.
It's not an illusion, because they got away with the fact that it was an illusion, because they said, yeah, that's because Earth is passing in the inside lane Mars, so that's like a horse passing another horse, and the impression will be that it goes backwards.
Yeah.
But no, it's much. In fact, it's much simpler in this way, and it's also more accurate, because the exact places where Mars is, they are exact. They are exactly as are observed. I must emphasize this. The Tychosium, this model you're now seeing, the interactive Tychosium 3D, is already at a level of precision that is quite, really, really, really very, very accurate, with all observations made in hundreds of years by hundreds of astronomers. All the tables, it respects all. You can ask, where is Mars in 1999, 1st of February? There it is, bang, okay? All the time. We've been checking this for years now, because my book came out 3 years ago. So I've been, double, triple checking Tychosium millions of times. And I've even found, old scriptures when Mars was in a place in an important time in ancient history, and there it is, exactly where they told us.
Right. So anyone can go on the program and wind the clock back to a famous conjunction and see it line up.
Precisely.
Exactly.
And you can also check the astronomical positions here on every object. Here we have, for example, Mars and every planet, and you can compare. Here up here you have the date and time, and you can just pause and you can see at this, what is it, 2008 in May.
Mm-hmm.
Yep.
We have this position of Mars, and you can compare that with, say, Stellarium or any planetarium, and it checks out.
And you also have the other moons. You can put the other moons in, can't you? Like Phobos and Jupiter's moons and whatnot.
No, we don't have. We don't have the Jupiter's moon. We have the Mars moons.
All right.
I think we have. Yeah.
We haven't come that far yet to have all the moons. I mean,
Right.
I
should say
around Jupiter.
I should say we've got it sort of zoomed in here, haven't we, Patrick? If you zoom out, you will find the outer planets, the gas giants. It's just
them as well. And I think it could be interesting as well if I start the simulation again to see how this. What this model suggests, and if we increase the speed, we will see it very clearly. That
you should run
as you see, both the inner planets and the outer planets are, so to speak, attached to the sun. They are following the sun while the sun orbits Earth.
So the sun is still a very important thing. It's a central magnet of the whole system. It's a magnetic system. Everything is there. These are magnets. And by the way, that's what Kepler believed. He said that they were magnets. But then came Newton and he said, well, gravity and he said, well, I'm turning things around. But they are magnets, obviously.
I mean, that's one of the questions that strikes me just looking at this is why doesn't the sun pull in Earth and Mars and whatnot? It's like how does this equilibrium exist?
Well, the equilibrium, I mean, if you read my book, you will see that at one stage I discovered another funny thing. The moon, our moon, has a period, 29.22 days. That's the most precise average period of the moon in which it returns to facing the sun. It's called the synodic period. And that's the period that the Maya people knew about, 29.22. If you multiply 29.22 by 4, you get Mercury's period, exactly, 116.88. If you multiply it by 20, you get Venus' period. If you multiply it by 25, you get Mars's period. By 150, Jupiter. And so 375, Saturn. The moon is the central axis of all our system. Our little moon is that important. Why would it be that important if we were just, the third planet out circling around the sun? In the third lane, just one of other planets. Why would the moon communicate with all the other planets as if it were the central drive shaft? The moon, our moon, is its central drive shaft for some reason. But you can see it's working here. We are looking at it. You can enlarge a bit maybe now to see the moon.
Yeah, sure. And I mean, this also. I mean, what you have here is Saturn and Jupiter, and this also would explain the retrogrades of those planets as physical. They are actually occurring because Jupiter and Saturn is orbiting the sun, while the sun is orbiting.
I know it looks strange at first. It looks strange. Why would they do this loop, loopy? But it works. It is the only way. Also, what the Taikos can claim is that it is the only simulator that agrees with the alignments between the planets and the stars. And how can I say that? Shall I explain this? Because this is one of the most important parts of the whole thing.
Absolutely.
Okay, let's take Mars. Mars was really the problem that Kepler couldn't, solve. He was desperate. Mars does a really funny thing. Mars returns. If let's say that you want to monitor Mars for many years, you're a very patient guy. You look at Mars one day, and you choose a star that Mars passes in front. Okay, you choose one star. Okay, let's call the star Deneb. Okay, you choose a star Deneb, and you start from there, and you wait. When will Mars return in front of star Deneb? It will take 707 days, more or less. 2-3 days, more or less. Okay, 707 on average. Once again, 707. And for 7 times, you will have to wait 707 days to see Mars returning in front of that star. But the 8th time, to complete the 15-year cycle of Mars, the 8th time, it will take only 546 days. Mars will return in front of Deneb the 8th time in 546 instead of 707. Jesus Christ, how could that happen in the Copernican version? You know, that's it. If we are going just on 2 lanes, you know, we are on the 3rd and Mars on the 4th. This could not happen. But you know how they made it work? Kind of work in the Copernicus system. Right. Well, what happens is that this short ESI, we call it, the empirical sidereal interval, which is 546 days. That happens when Earth is on the one side and then on the other side of its orbit, supposed orbit around the sun. So, yes, but if we have moved 300 million kilometers because that's the width of the supposed orbit of Earth around the sun, if we have moved laterally by 300 million kilometers, how can Mars face the same star? I mean, please understand. It's as if you put your finger in front of your face and then you move and you look at the distant tree. And you move for 1 kilometer. Will your finger be in front of that tree? No, it won't be aligned with the tree, right? Mm. But here we are talking about 300 million kilometers, and still that happens in reality. So that's when Patrik sent me the first version of the Tychosium, which was still in its first stages of development, but already the first thing I checked was if Mars would do this very funny cycle that is 7 times 707 days and the 8th time 546. Yeah. Well, can you imagine? I fell off my chair when it actually happened. The Tychosium shows this. You can check it out for yourself. It worked. It is because in 15 years, which is 15 years is a cycle where Mars returns to the same place in the sky. So it's a very famous cycle of Mars. In this 15-year cycle, the last loop of that cycle closes before because it doesn't reconjunct, at the same place because it's a spirographic thing. Oh yeah, now you're showing the first.
Yeah, I'm showing the old one. Yeah.
Yeah, but to try to explain, maybe you should go back to the new one, and because what is this very short 546 cycle? It's just that's the only time where Mars misses its retrograde. So, it will get back on the same line of sight to that star. Let's see if we can explain it.
Yeah, if we...
Maybe you can go faster. You can go faster.
It's coming in there.
Yeah.
Hmm. All right. Yeah. Okay.
Tell me when to stop.
Yeah, it's hard even for me. But it's okay. No. There's a point where you can... well, it's in the book. I've done an example to show exactly. I actually, overlaid those eight periods, 7 times 707 and 1 times 45. I have overlaid them, and you can draw a line to one star, and the Mars will always return on that exact line of sight. It's hard to show here right now but you can see the Mars is always doing those loops, and there is a little gap. Well, now we don't see all of them for some reason because the program doesn't remember a couple of them, but 2 of them are closer to each other, and so anyway,
that's the shorter interval, the 500 and whatever day interval.
The famous short ESI. Wow. And that was something I read in a paper of very, very, very academic astronomers, they had studied the Maya numbers, and they were talking about this short ESI. But the article, this academic article, doesn't end with any conclusion. They just say, yeah, the Maya knew that Mars had this strange, much shorter period, but they just end there and don't make any. It should have, only that paper should have destroyed the Copernican model.
Yeah, it seems like all these ancient civilizations generally had a geocentric model, and then when Kepler comes along, it was interesting how you talked about the eclipses, the elliptical orbits, and the varying speeds. It sounds as if they've predetermined what the model's going to be and then just tweak the maths to make it fit.
Yes, it's an ad hoc type of procedure. It's what science doesn't want to be. I mean, it's exactly the opposite of science. You can't just adapt. If something doesn't work for you, you have an idea. You can't just say, well, maybe I can when I can accelerate that thing and slow it down so then it fits into my model. That's what Kepler did. And even more damning is that the guy who finally translated in recent years, in the 1980s, the guy who translated Kepler's book, the famous Astronomia Nova, he even showed that Kepler he lied. I mean, he fumbled his data. He made it look like in the beginning of the book he has some numbers, and then at the end of the book he changes those numbers. He deceived us. So Kepler, who is so famous, is to me a complete clown. He's the biggest clown of astronomy, and I can say that.
Yeah.
Okay.
Simon, without ellipses, and this is all based on circular orbits, I'm sort of gathering. How is seasonality explained and equinoxes and things?
Everything is explained with the seasons. It's there's no problem with that. The seasons are explained because Earth is tilted. Now you can show it laterally.
I can, because I mean in this model it's
show them
the Earth has its tilt, and
June and December. Just show them June and December, because in June, okay, Earth is tilted by 23 degrees approximately.
Let me ask
so
the reason.
You can go to June now.
Just a moment.
And when the sun is on one side and we are tilted towards the sun, we have summer, and when we are tilted away from the sun, we have a winter. That's very easy.
Oh, so that tilt is maintained in this model then? It's just it wasn't mentioned.
Yes, of course. I mean, there are many things that I maintain. I'm not trying to make fools of all astronomers. There are some things that I maintained, like the distances between the planets. Our planets, but not with the stars. We'll get to that later. But I don't accept the distances to the stars. And I will explain why. The stars are much, much closer than believed.
So, I mean, here we have Earth in June, and it's leaning towards the sun.
So the northern hemisphere will be hotter, of course.
Yeah, and then if we go to December, then we have winter because the Earth is leaning.
Yeah, so the tilt, maintaining the tilt takes care of seasonality and like the land of the midnight sun and all those sort of effects.
It's precisely the same, but this model is much simpler and more plausible because. I mean, the model we have today, it's quite a few motions of Earth, and the strangest motion of them all is the so-called wobble.
Precession.
The processional wobble, and that is not needed in this model because we have the Earth's own orbit.
Show it with show it with the mouse. Show the direction of the PVP orbits. The Earth is going.
Yeah, sure.
Yeah, this is something that particularly interests me as a fan of ancient history, is the precession of the equinoxes.
All right,
which
that's
doesn't seem to be sufficiently explained in the standard model.
That's humbly speaking. Sorry, who am I speaking to?
It's Phil.
Oh, Phil. Oh, sorry. The precession is explained officially by the idea that the Earth would wobble. Okay, it would wobble very slowly in 26,000 years.
Yep.
Wobble in the opposite direction of its rotation, which is physically very, very strange. You know, if you have a spinning top, like, you know, the kids are playing with a spinning top, when it starts falling, it won't wobble in the opposite direction of its rotation. Okay, but Earth would do that according to Copernicus.
And according to Wikipedia as well, because I checked today, they say in the Wikipedia they use the example you did of a spinning top. Yes. And yet the wobble acts in the opposite direction.
Yes, the NASA uses it. And you know what? On the Italian Wikipedia, I once noticed, they've deleted it now, but I once noticed a big red line saying, yes, but this has never been explained physically. Why this could happen? So I screenshotted that because there was someone who said, how could it possibly wobble in the opposite direction of its rotation? Anyway, so the only thing I will humbly say now, I have only discovered one more thing than my master Tycho Brahe. I consider myself just, you know, the little guy who came 400 years later and found the missing piece of the puzzle. So the missing piece of the puzzle that Tycho Brahe could not have known at the time was that Earth is not immobile like as he thought. He thought Earth was totally immobile. It actually moves, but it moves extremely slowly around what I call the PVP orbit. Why do I call it a PVP orbit? PVP, because now, today, we are under Polaris, our North Star, Polaris. Mm-hmm. In about half of 25,000 years, we'll be on the other side, and we will be towards Vega. You see Vega? You see Polaris and Vega? Okay, that we will have. Our North Star is always changing. I mean, that's documented. Everyone has documented that. The Egyptians had another northern star 5,000 years ago. That was Tuban. You can see Tuban here on the screen.
Yeah, there we have Tuban. So like let me show you now. If I step 2,000 years back in time in this model, if I put a 0 here instead of a 2, and now watch the Earth and see what happens. You see?
Mm-hmm. Yep. So that's the new
2,000 years ago. We had no north.
Oh, it's in between, right?
Yeah, it was in between. So
you have to go 5,000 years, and you will see.
So if I put minus 5,000 here.
Minus 5,000.
No.
Minus 5,000.
Minus 3,000.
Minus 3,000. Yeah.
Yeah. There you go. So now Earth is approaching.
But our stars are still provisional. We haven't still got them.
Yeah, it must be incredibly difficult to try and map the stars so accurately. Yeah, but we get the idea though.
Mm-hmm. Yeah, these stars are still a very, we haven't finished. I mean, it's still a work in progress, of course.
Yeah.
So the stars are just some points that Patrik has put, but they can, I mean, if you know how to work the Taikos, I mean, it's not cheating. Just if you know how it really works, it actually matches up pretty well. And
just to explain this, I have brought in the celestial coordinates, and but I mean, as you see, the stars are much closer than they actually are. But that's also I can, if we zoom out here, I can bring them out. But I mean, since we have
They are pretty far away, but
yeah.
they are pretty
But
far
I
away.
mean, they will still be on the same position on the celestial sphere, no matter how far or close there are. If you
Right.
follow what I mean.
Yeah.
Yeah.
So
Yeah.
they will still remain their position in relation to us.
I've tried to make them as distant as they supposed to be, and that's when it works best. So I think we are on the right track, even with the stars. But what we are really on the right track with is the alignments that have been recorded. You know, there are so many tables you can consult, and you can see when was. And especially, okay, first of all, between our planets, Jupiter, Saturn conjunctions are very famous conjunctions. They all work back in time for thousands of years in the Taikos. The solar eclipses and lunar eclipses, they are all work perfectly. Pretty much perfectly. The only problem I'm still working on is sometimes the moon can be bits lower, a little bit higher. I mean, the height, but not the position, the lateral position. That's perfect.
Wow.
You see what I mean?
Yeah.
Because the first thing I really wanted to show that we don't need any accelerating or decelerating planets. They will come back as expected there. Another thing I verified is all the transits of Mercury and Venus in front of the disk of the sun.
Right. Yeah.
Yeah, well, you know that Venus has only transited 10 times in the last 500 years or something. And well, those 10 times, very rare occasions, they all check up. They all check out.
It's incredible, to be honest, that it works so well, yet it's so fundamentally different from.
Yes. I mean,
Yeah,
I was amazed myself, of course, when this
Can I
started
get
working.
can I say something, Simon?
Mm-hmm.
Okay. No, yeah, I just wanted to hear about you. What do you think about this? I mean, it's pretty convincing, right? But if it is, it kind of raises a lot of other questions, right?
I think it says. I think, you know, when you think about sort of the change from the Earth being the center of things to the sun, and all sort of like the consequences of that culturally and in terms of religion and all the rest of it, it's quite an interesting thing to put it back in the middle, I suppose. That's what I've been thinking about. And you said something. So you said, I think it was Simon. You said that it's you think of it as a magnetic system. Is that what you said? So are you kind of saying that the Earth is like a giant magnet then, and kind of pulling everything around it?
I you know what I said sometimes I think in the few conferences I've done some in America and some in Sweden. I think I said at least once that please leave Newton at the door. We don't need Newton right now. We don't need physical explanation. We need to verify first of all observations versus tables of observations that we can verify, that we have documented, that are there with actual reality. It's all about being an empirical scientist here. Because
I agree,
geometry,
Simon.
if we don't get the geometry right, we shouldn't even start making suppositions of how it works.
No, I agree, Simon. I think what you sometimes say, you shouldn't put the carriage in front of the horse.
Yeah, exactly.
What I mean is that first we need to actually figure out and accept the geometry of our solar system, how things actually move. And then we can start to think about why it moves as it does. What kind of forces are at play?
You said it's exactly what I was trying to say. Thank you.
And I mean, the amazing thing here, when you start to think about this, how it actually could be, is that, I mean, for thousands of years, astronomers has assumed that the Earth is very static, that it doesn't move much. And why have they done that? Yes, because the stars doesn't shift
Don't
during the
shift.
year
Yeah.
very much. I mean, you only have the precession.
Yeah, and that's a very subtle motion.
Yeah, they knew about it, but exactly, it's very subtle.
Yeah.
And the funny thing with this is that, I mean, the explanation today in the heliocentric models as to why the stars doesn't move during the year is because they are so far away, you know.
Yeah.
So they do move, but we can't see it.
They all have their proper motions too. They have some proper motion, and that's the all stars move a little bit about the sky, very little. But what's important to understand is that all stars, I mean, what is precession? Many people don't even know what precession is. It's a very simple thing. Precession is the fact that every single year, if you look at the sky, you're very patient, you stay there in the same place, and you look at the sky, you choose one star of your liking, and you say, what's that star going, where is this star going to be next year? Well, it's going to be slightly to the left.
I mean, the problem is that from
50.3 arc seconds to the left, 50.3.
Yeah.
Every year it will go to the left. It will go to the left. Well, and that's exactly what we're seeing here in this animation. Because our Earth, even if you can't see it because it moves so slowly, our Earth is moving clockwise to the right. That's why the stars are moving to the left, okay? Is that easy enough? Even a kid can understand this. If we are moving to the right, the stars will be moving to the left, okay?
Yeah.
Make the PVP orbits larger, please, Patrik. Okay? What you're seeing here, you can't see the Earth moving because it moves so slowly. It's moving from left to right. Okay? At 1.6 kilometers an hour, 1 mile per hour, practically.
1 mile an hour orbit.
That's the speed, the
right,
translational
okay, I can see it now.
speed of Earth. Earth is moving at that slowly. How could I even come to that conclusion? I explain it in my book. And it's hard to explain to you right now, but I could calculate the diameter of the PVP orbits by using other planetariums, just by seeing how long it takes for the sun to move to one star to the other, and taking that and extrapolating how large, how wide our own orbit is.
Yeah.
And that's explained in my book. It's really hard to explain here on the radio.
One of the things that's quite striking, sorry to jump in there, but I just saw it on the screen, is how close Venus comes. I mean, it's almost like a couple of the distances from the moon away.
It really comes, it's the closest planet.
It's a hop, skip, and a jump at that point, isn't it?
It comes very close. Yep. It comes to 0.2 AU. It's the closest passing planet, and that's accepted by everyone. I mean,
handy time for sending a probe out, isn't it? I guess.
You know, there's so many things that still remain from the old. The established ideas. Venus comes closest. There's nothing really, crazy about this. It's just that it's amazingly. I respect so many things with this. I'm not, it's not like a crazy idea completely, out of the blue. It absolutely works, and the basic things are respected. Venus, look at how close Venus comes.
Yeah,
now.
there it is. Yeah.
Yes. Well, it does that, and everyone accepts that. It does that. So there's nothing really, nothing that is in conflict with the main, knowledge or observations that have been made by the best astronomers in the world.
What happens to the moon when Venus gets that close? Because it almost pinches it.
No, I mean it's still, the moon is only 400,000 kilometers away, and Venus comes at what is it now? Well, it's much further anyway. It's 0.28 AU, which is let's see now. 0.28 20. You.
Yeah,
Like 41 million. But I want to go to another thing that I really, that's another thing that made me jump up in my chair.
Yeah.
Because what I discovered thanks to this Tychosium, which I could never have discovered before the Tychosium came to life, is that when Mars comes closest to Earth, sometimes it comes very close to Earth, okay? Like in August 28, 2003, it came as close as it has been for many 60,000 years. All astronomy sites were celebrating Mars coming closest to Earth, okay? Yeah. And you know what? It came at 56.6 million kilometers from Earth. What is 56.6 million kilometers? It is exactly half of the diameter. It's actually exactly the radius of my PVP orbit.
Wow.
Yes.
That's the precessional orbit that the Earth is doing very slowly at 1 mile an hour.
You see now, Mars is now, well, case,
look, it's normal. It's almost.
Yeah. Sometimes it comes when it comes closest. It comes, in this case, in this year here where we are now, it's not exactly like that, but in other years, it will come exactly in the middle of my PVP orbit, which is 113.2 million kilometers. 56.6 is exactly half.
Wow. It's amazing. It's another weird coincidence.
Yes.
I mean, the problem you have, I think, Simon and Patrick, just speaking for myself, as someone who's grown up with a UK state school education, it's classed as sort of a given. It's knowledge that is assumed, and it's not just in the teaching in the realm of education. It's throughout the media. Every movie you see, every TV show reinforces the heliocentric model, and so we've all been programmed, for 40 years in a certain way of believing how things work.
Yeah, well, we're realizing this now, aren't we, with this other hoax?
Yeah, and if I may, Simon.
Please.
Okay. Thanks.
Sorry. Yeah.
No, it's so interesting as well because I mean, if we look historically, we had another model a couple of 100 years ago that was sacred. That was the Ptolemaic, the Aristotelian model, and it was with the crystalline spheres, and when this came under question, it became a very worrisome period in the world, But I mean, it wasn't correct, and I mean the biggest error in that model was that it was assumed that the Earth was the immobile center of the universe. I mean they assumed that the universe rotated around a completely stationary Earth.
Yeah.
And interestingly enough, we are now in another way of looking at things with the sun in the middle. That doesn't seem to compare very well with the observations. So
it
makes you wonder.
It simply does not work. It's optically impossible. The Copernicus system is impossible.
If I may, Simon, can I show you an interesting thing here? Because, I mean, when this was under discussion in the 17th century, Tycho Brahe said something about the Copernican heliocentric model. I mean, Tycho Brahe, he thought the idea that it was the Earth that rotated and not the universe was very interesting. But it was a politically difficult question at the time because the church wouldn't accept that. So I think he probably avoided that question for political reasons. Yeah. But what he also said about the Copernican model that he didn't like the idea that Earth would
idea.
Thank you. Idea that the Earth would orbit the sun, because that would mean that the stars would have to be extremely large and extremely far away. He didn't see it as geometrically possible, because I mean, as we said, during the year the stars are stationary in the sky; they don't move. And I can show you here in the model what a heliocentric model, how it would have to.
What it implies. It implies what the Copernican model implies, that the stars would also be. Okay, show it, please. It's wonderful.
Yeah, thanks. So, I mean, if we have this moving here, the model as with the Earth stationary, but I have this function where you can shift the view, so you can make heliocentric model out of this. So if I change the target here to the sun, so now you see everything is centered around the sun, right? Yeah. So we have here we have a heliocentric model.
All the stars are moving.
Yeah.
Yes.
That is what's required. So we need this. This needs a new type of geocentrism, where the universe follows the Earth around the sun.
Yeah, it's really it's more wacky than you can even imagine.
You raised a good point, Patrik, there about the political climate when Tycho Brahe was doing all this stuff, and the point of the church. And you've got to bear in mind that if making the sun the center of the universe, it would have been. I'm thinking of like solar deities and solar worship and all that stuff that came before the church, for the thousands of years before the church. I don't know. It's an interesting flip. Why I'd like to know, why it happened at that particular time.
Can I come back and explain this? Yeah, I mean, it's all about Galileo.
Yeah.
Galileo Galilei, he was the most arrogant piece of shit that science has ever known. He was so arrogant. He actually said that any new discovery with my telescope should go through me. I have to, vet it before it can be shown to be true. And he was the most arrogant prick you could ever imagine. And he was the big promoter of Copernicus. He was a friend of the Pope. The whole story that he was put in house arrest is a joke. He was put in a beautiful mansion of some friend of his, of the Pope, and he suffered nothing. And whereas Giordano Bruno, he was burned at the stake.
Yeah.
Okay, so there's a big difference to be burned at the stake or live in a beautiful mansion, even though he was against the church. So Galileo was some kind of really, really weird guy. I mean, really spooky guy. But we all know Galileo, we all know Kepler, we all know Einstein, we all know these superstars of astronomy. And Newton, of course, and we're stuck with these guys. We can't even dare question their postulations, because they were only postulations. They didn't have any proof, and I want to say one thing: there is no scientific proof that has ever been done of the motion of Earth around the sun. I mean, in the Copernicus system, do you understand that officially they are telling us that our planet Earth, is going around the sun at 107,000 kilometers an hour. You can translate that in miles per hour, but 107,000 kilometers an hour, you know what that is? That's 90 times the speed of sound. That's what we are supposed to be doing now. Right now, you're sitting there in your room, and we are sitting here. We are going at 90 times the speed of sound. All right. So, okay. So I accept that the Earth spins around its axis at 1,600 kilometers an hour, but I accept that because we have an atmosphere which destroys all the meteors that come into us. So we are very, very attached with our atmosphere is our protective layer. We have meteors coming into and they burn up. Well, you have meteor showers so every year. We can see that. That's verifiable. We can see meteors and we can see them burning up. So there is some sort of strange thing that we don't understand, because we don't understand one thing. Why doesn't the atmosphere of our Earth sort of equalize with the vacuum of space? Okay, and that's an argument that flat earthers will bring up. Flat earthers like to say that. Well, yes, it's strange. We don't know. But we must accept that we don't know it, and we should work on it. But the fact that we are rotating because the 1,600 kilometers an hour figure is for one guy sitting on the equator of Earth. Whereas if you are at the North Pole, you're going at 0 kilometers an hour. You're just rotating around yourself, almost at 0. Okay. So it's not very fast. It takes 24 hours for a planet to revolve once. Well,
yeah, and I'm having.
I finish, Patrik. Take an orange tonight. You go in your kitchen. You take an orange, and you sit there for 24 hours, and you put an ant. Put an ant on your orange, and see if the ant will be thrown away by the centrifugal force. It won't. The ant will stay there.
Yeah, okay. That's correct. And I'm having Tychosium in real time now. So 1 second equals 1 second, and you see it's not happening much. We don't see much of the very fast rotation of Earth here. But if I increase it a little bit, now 1 second equals 1 minute. Now it's detectable.
Right. Yeah.
So,
yeah, it sounds fast, doesn't it? 1,600 miles an hour, whatever. But because of the size of the globe, you can account for that. Yeah. What are the wider implications, do you think, for this model?
Well, hopefully, since this is a model that Simon has developed that actually agrees with all known observations and experiments as opposed to the current one, we hope it eventually will be accepted. But I mean, that is that will take some time, and as you probably understand, it raises a lot of questions.
Yeah, well, I mean, the first one that comes to mind is: do other people know about this and they're not telling us?
Well, obviously, first, for this model to be accepted, NASA has to collapse.
Yep.
The idea that
never
NASA
a straight
goes
answer.
Because why hasn't NASA ever sent a satellite full of cameras and just place it in a place where it gives us day by day the picture of our solar system?
Oh, right. So would that have to be sort of far out or straight up?
They say they can go as far as, they have some probes. Apparently they have gone to other galaxies.
Oh, Voyager, yeah.
Voyager
just left,
they can place anything. They can place geostationary satellites, you see, just above Paris or London, and they will stay there. They can send them up at 28,000 kilometers an hour, but they can break them and just stop exactly where they want.
You'd only have had a brownie box camera or something on there, Voyager 2. The technology wasn't there for that. But maybe.
Why don't we have, I mean, seriously, guys, why doesn't NASA have a satellite that's placed in a proper distance to show us that the Copernicus system is what it is, what they tell us it is? Why? They claim they show us pictures of other galaxies which are really far away, and with details of how they spin around, and they are all they're all trochoids. They're all going around, just like I'm saying we are doing. And you know what? There is a study from 2007 or 2008, or even more recent, which I have in my book. Of course, I've taken, where they show astronomers who have looked at binary systems, and they see them doing all these spirograph patterns. All the binary systems are doing spirograph patterns. So why shouldn't we do that?
That's one of the key takeaways that's been for me, is that it seems that more and more stars are going to be discovered to be binaries, and just the probability of our system not being a binary goes up each time another one's identified, doesn't it?
Yes.
And if it is a binary, then what is the
what's the other star?
the partner? Yeah.
Look, I can tell you very confidently that 100% of the stars we can see with our naked eye are binary. 100%.
Do you think that some of these exoplanets that are being identified could be the binary partners? Then
Exoplanet. Haven't you seen in the newspapers? They regularly tell you, "Oh, well, we found some new exoplanets around that star." Well, that's because they're finding more and more things. They're finding more binary systems with moons and stuff, and they're calling them exoplanets. But no one is saying we found another binary system. They're trying. They're trying to. Of course, they're trying to protect this problem. It's a big problem. It's a collapse of science, of astronomy. If they would never admit that all the stars are binary.
No, and speaking of that, Simon, if I may interject regarding science, because I mean, as you know, guys, physics and astronomy, or at least theoretical physics and astronomy, it's pretty intertwined. You talk to I listened to one of your shows where you talked to an astrophysicist, and you had this guy Mark on the show as well, as I listened to, and I mean, what's so interesting to see about this, if you have this perspective, if you open to the question that we may not have accurate solar system model, and because one thing that happened in the late 19th century and the beginning of the 20th century was that they performed an experiment where they wanted to confirm Earth's speed around the sun, and it was called the Michelson-Morley experiment. Have you heard about that?
No.
Oh,
that's interesting, because that was an experiment where when the paradigm or the view in physics was ether physics.
Yes, all right.
So they wanted to measure the difference of the light, how light was affected because of Earth's orbit around the sun. But the problem that occurred was that they couldn't measure what they expected.
They were looking for the 107,000 kilometers an hour speed of Earth. Okay,
Yeah.
let's make it simple.
Yeah.
Let's make it simple. They were looking for 107,000 kilometers. They found almost nothing, or something very, very small. But they did find something. But it was discarded like instrument error. They did find something. So, but they all said, "Oh yeah, it was the most failed experiment in the history of science." They call it now. And Einstein said, "Oh well, okay, I know why this happens. It's because ether does not exist." That was his way of getting out of the problem. So Einstein was the biggest clown ever.
Yeah, I would say so. And the amazing thing here, guys, if I may, Simon, is that
to protect the Copernicus system.
Yeah, exactly. I would say we have changed physics so that it fits this model, and that causes a big problem in physics, because they have problems now. Because if you just accept that Earth doesn't move very much in the ether, then ether physics becomes crystal clear and harmonious. But if you can't accept that, if you have to explain away the ether or make it fit with this model, then you have a problem. So and I agree with Simon. I think the reason with the thing Einstein did was to salvage the heliocentric Copernican model by explaining away working physics.
And he wasn't the only one. Then there was Bradley, the astronomer royal of the Royal Society, who came up with another explanation. Because he was a guy who looked at a northern star in the Draco constellation, and he watched this star for many months, and it moved in a way that was completely disagreed with the whole theory of heliocentrism. Why did he disagree? Well, he saw the star do a loop, a star that he was looking at over several months, over a year. It would do a trochoid. You know what a trochoid is? It's like, it's a loop. It's a loopy loop. It's a loop, okay? Just like the loops you see on. Well, you know why? You know why he saw that? Well, when we saw that, he said, "Oh, well, I have to find an explanation for this." So he came up with the idea of aberration of light, because the aberration of light would be because the light rays, since we are moving very fast around the sun, the light rays would come skewed, and it's just like raindrops falling on the window of your car. And we have to adjust our telescopes in order to understand, But, this star was actually doing a loop. Well, why do all, and then he checked other stars, and they all did the same thing. Well, that's because, and maybe Patrik can bring up, or maybe I should do it. There is a chapter in my book where I explain this very simply. What an earthly observer will do during a year, since we are rotating and moving slightly forwards, we will do a trochoid. What is a trochoid?
Which chapter is it, Simon? If I
okay, aberration of light. Yeah, 34.
34.
Ah, nice. Can bring it up. So yeah, scroll down. Yes, okay, that's okay. Now the lower graphic here, well, okay, but the white trajectory you see here.
Yeah.
You see the white trajectory?
Yes.
Yeah.
That is the trajectory that an earthly observer will do in 1 year. Because an observer that every night at midnight looks at a star and takes a picture. So if he takes a picture at 1, you see 1 up here.
Mm-hmm. Yeah.
And he keeps taking a picture of the same star at midnight every night, he will finally see the star doing exactly what he's doing. He's doing this pattern. So if he has a plate, photographic plate, and the star will fall down on his plate, it will do this funny trochoid, because we are advancing from left to right. You see the Earth. This is a graphic I did to show that Earth is moving by 14,000 kilometers every year. It doesn't move more than 14,000 kilometers, a bit more than its own diameter.
Yeah.
So the Earth is moving at 1 mile per hour. In 1 year, it will do just 14,000 kilometers. But an observer, say in London, where I did this example, he will be brought around this trochoid. And so each picture he will take will come on his plate in this shape. Now you can scroll down Patrik, and you can show. Oh, maybe next chapter I'll show how they exactly see the stars. I think it's the next chapter. Yeah. Where is the chapter where I show how Vega? Wait.
The mystery of the negative stellar parallax.
Yeah, that's an
Yeah.
interesting as well.
Yeah, that's one of the. This is one of the best
title.
points we have. This is one
Yeah.
of the best arguments we have. This is one of the best, really.
Yeah.
Because shall we go there? Shall we go to the stellar parallax?
Yeah, let's do that one because
Yeah, because it can be explained maybe in an easier way.
Yeah, good.
Yeah, because we're quite simple people.
Yeah.
We are all simple people, but it's just that you have to get into the geometrics and. Anyway, here this graphic we're looking at is if it were true. This is a Copernican graphic. Okay.
Yep.
So the guy up there, he says, I am obviously moving from right to left in relation to the stars. Okay. And the guy on the bottom, he says the same thing. I am obviously moving from right to left in relation to the stars. Okay. If Earth would be going around the sun as believed.
Yes.
So the stars will always have a parallax in one direction, not the other. We never change direction. I mean, we are going on the same direction all the time. So the parallax should be always positive. That's what's called positive parallax. In astronomical terms, that is positive parallax. But the problem is that for hundreds of years, they have detected negative parallax. That is, the stars seem to move the wrong way. Okay? And as many as 25% of the stars move the wrong way. And 26% move the right way, but 25% the wrong way. And the remaining 50% didn't move at all. When I say move, it means, the lateral displacement. This is when they are measuring a nearby star in relation to further away stars. Okay, that's a parallax discussion. They're looking at the nearby stars and seeing if they move, because they should move. If we are going around the sun, we are moving around an orbit which is 300 million kilometers wide. Then the closest stars should move, like a tree in your car that's closer to your car and a mountain behind it. Okay, it's parallax. So the mystery of negative parallax has never been solved. It's just what they say is that, well, when they found even here we see an old, it's from an old book from 1878. Even these measurements of the annual parallax of the fixed stars, it sometimes happens that the astronomer finds his observations to give a negative parallax. To understand what this means, blah, blah, blah. And then such a paradoxical result can arise only from errors of observation. So they explain it away by errors of observation, but they saw negative parallax. Well, in the Taikos, let's go straight to the Taikos explanation, which is down here. Wait. This is a rate that you can see on the tables of the European Space Agency. They say that there are 29% positive parallaxes. They say that negative parallaxes 25%, and zero parallaxes are almost 50. Like there are, this is
they don't recognize these as negative parallaxes. They say they are measuring errors or proper
25% error.
Yeah,
but
only those. No one of those, but only these.
But they're still boasting. But they're still boasting that they have an enormous, incredible accuracy now with the new satellites that are measuring this. Okay, here we go. This graphic, guys, will go down in history.
Hopefully,
this is for kids. This is a graphic for kids. Good. But you must take some time and look at this. Now, please understand, if Earth is moving almost in a straight line, okay, you see, it's moving, in hundreds of years, it's moving it's been always moving like, from right to left on this blue line, you see.
Yep.
Okay, so it's basically moving in a straight line, because in hundreds of years, of course, it's always with bending because it's going around an orbit, but in the thousands of years that we have been living in, we have only been looking at the stars like this. So, Joe, you see Joe up there? Mm-hmm. He says, I've been drifting from left to right in the last 6 months. Okay? Mm-hmm. And he's looking at a nearby star. See, you see the nearby star above Joe?
Yep.
And so he looks at the nearby star and compares it with the distant stars behind. And that star will move in a certain direction. Whereas Jim, below, on the other side of Earth, he will look on the other quadrant of our skies, and he will see the stars moving from right to left, not from left to right.
This is also, you need to understand that during the summer and winter, the sun is on the other side, on opposite sides of Earth. So that's why you see the stars drifting or the parallaxes.
Yes, because it changes in nighttime. Nighttime is, on one side is summer, the other side is winter. Yeah. And then, but no, wait, let me finish. Yeah. What about the 46% of no parallax, stars that don't seem to move at all in relation to the distant ones? What about them? Well, look, if both Joe and Jim are going away from the stars to the left of this graphic, they're not going to see any difference of the nearby star in relation to the further ones.
Right,
there
yeah.
will be no parallax. And the same with the star he's going against. They are going against. They're going towards them. If you walk towards this tree, and behind the tree you have a mountain, the tree and the mountain will remain aligned. Okay.
Yeah. So the zero parallax stars are the stars on the plane of the ecliptic, essentially.
Is explained. The 46% officially claimed on the tables is explained by this little graphic.
And it's 46%. It sounds right. If it was 10% zero parallax, this wouldn't work. The fact that it's half, and then you have a quarter above and a quarter below, as above, so below. It's the old Hermetic axiom. Yeah, it's right. It makes sense to me.
Okay,
love it. Absolutely love it. I'm gonna uninstall Stellarium as soon as we're finished. And
no, please. Keep it, because Stellarium is absolutely. Oh, it's so correct in some ways, but then it gets it has problems.
Yeah, I think that's important to explain. I mean, what's going on there, because I mean, Stellarium is observationally correct, but why is it? Because it is showing the skies from a geocentric viewpoint.
Yeah, it's just the observation.
You can never zoom out from Stellarium and look at the system from a helicopter view as you can do in Tychosium.
Yeah, I was being facetious.
What you will never find, guys, is heliocentric Copernican orrery, where the stars are accurately represented. Because you can make a Copernican heliocentric orrery work if you only have the planets moving in
of our own solar system.
Yeah, right. but you can't make the planets be in front of the stars. They observe
the alignments get off whack. They get totally off whack, and the only excuse they have for that is that the stars are so far away.
Yeah.
It's so far away. Yeah. That's the only explanation they have.
Well, I mean, we got to wrap up. We've blown well over time. I mean, we could go through this all night, but we've got work in the morning.
To talk with you guys, really.
Yeah. I think, is there any final thoughts you want to add, Simon or Patrick?
Patrick?
Yeah, I mean, I hope people that are interested in this takes a good look at it, because as I told you in the beginning, I mean, I've found this very unlikely. Now I've worked with it for 4 years now.
Yeah.
And it checks out. And I mean, if you talk about science and scientific evidence, one of the strongest evidence you can have is a demonstration. Well, here is the demonstration.
Yeah, there it is.
And we have it with the astronomical positions as well. And as I said before, you won't find a Copernican or heliocentric orrery where you can see the planets move and be in correct relation with the stars. And there is a simple reason for that, and I showed you that before, because it's geometrically impossible. The heliocentric model is geometrically impossible. Yes.
Yep.
So that's my final word.
Nice.
That was a good final word.
Yeah.
Do you want to add anything, Simon, before we play ourselves out?
No, I just want to thank you for taking your time and watching at our work. We are working like crazy. We are very enthusiastic about it, of course.
Yeah.
And I apologize to those who may think that, we are too enthusiastic, but we really believe in this because it checks out. That's what Patrick says. And I know what I'm talking about because I've been studying the Copernicus system very, very deeply before I started even this. So I know what the Copernicus system says, and I know what the Tycho Brahe system says. And the only one that works is this one, which is Tycho Brahe. And why is Tycho Brahe so unknown to the people in the world? Maybe, that's for conspiracy theorists to explain,
Heretic.
There's a book called Heavenly Intrigue, which written by a couple, Joshua Gilder and Anne-Marie Gilder, which explains all the history of Tycho Brahe and concludes that Kepler actually poisoned his master.
Yes, I was reading about that. Yeah, died in suspicious circumstances.
Yeah. So that's for conspiracy theories to munch on.
Yeah,
but I don't want to go there. I'm.
I'll go there. I'll go there. Taught him everything he knew. It's like the Emperor in Star Wars.
Yeah.
But I think we realized even in the last few years how much the powers that be wish us to stay ignorant.
Yeah.
Okay, so please meditate on that thing. They wish us to not be learned, and that's their plan. And even if you've studied biology, it's bullshit. So the whole thing. So. Yeah.
Well, on that note, thanks for coming, guys. We've really enjoyed it.
Yeah,
and
really good.
Stay on the line for us while we play ourselves out.
Yeah.
And Eavesdroppers, www.taikos.info. That's TYCHOS. Link in the description as always. And go and play with this model that Patrick's built. It's good fun. And then test it. Don't take our word for it. Look up some conjunctions. Test it to breaking point and see what you think.
That's science.
That's how science works. The proof is in the pudding.
Yeah.
We'll catch you on the flip side. Don't touch that dial.